Okay, so the video file from Monday's class didn't make it. The program crashed, so I'm going to put together just a review of Monday's class. And what I'll do is I'll ask a question and then I'll say pause here, and if you want to think about that and try to answer it before I do, then you can pause the video. And so whenever I say pause here, I'm just going to keep on going and then leave it up to you to pause to think. Alright, so we started by reviewing constant rate of change, and the first question I asked was, so if two quantities x and y change together in constant rate of change mathematically, what was our definition of that mathematically? You could pause here. So our definition of that was that changes in one quantity are proportional to changes in the other. And there were two powerful implications of this idea that changes in one quantity are proportional to the changes in the other, two that we used. So can you think of the two different kind of implications of this proportionality of changes? The first one is that every change in y is a constant multiple of its corresponding change in x, and the second was that every change in y has the same relative size to changes in x, and that relative size, or that ratio of delta y to delta x, that is our constant rate of change. So this quotient is telling us how many times greater are our changes in y compared to our changes in x, or the relative size of changes in y to changes in x. And that ratio is the constant rate of change. Okay, review of slope. The first question is how is slope calculated? And so you've all had some kind of algebra in your past, and you remembered that slope was the change in y over the change in x, or y2 minus y1 over x2 minus x1. But now we know that the difference between two y coordinates, or two y values of the y quantity, is delta y, and change in x, or x2 minus x1, is the change in x. So slope, that value of slope, is really, it's that constant rate of change that we just talked about. It's the relative size of changes in y to changes in x. Okay, so here in this picture, change in y maybe looks like 0.8 of the change in x, or y is increasing 0.8 times as fast as x. As x increases, y increases 0.8 times as fast, as an estimate. So how many changes in x and y exist here? In this picture, how many changes in x and y can we talk about? Well, while there's only one represented, one set of delta x and delta y, there are changes in, we're in command here. We can pick any point, and we can pick any change in x that we want. And for that change in x, we'll call this delta x1, there is a corresponding change in y, delta y1. Okay, I can start at this point where this one ends. I'll call that delta x2. So for any delta x, there's a corresponding change in y. Okay? How would we find, say, call this delta y3. What does delta y3 equal? How would you find the value of delta y3? Well, this goes back to our idea of constant rate of change, that any change in the y quantity is a constant multiple of the corresponding change in the x quantity. So we would need to identify this change right here that was associated with that change in y. We'll call it delta x3. And then the corresponding change in y would just be k delta x3, and we know that that k is the value of the slope. We could find it if we knew any two changes that correspond, take their ratio, that gives us the slope. And so now any delta y, every and any delta y, is k times its corresponding change of x. Okay, so this is just showing that there are an infinite number of, so back to our question, there are an infinite number of changes in x and changes in y that we could represent on this graph. We can start at any point, we can pick any delta x, and there'll be a corresponding delta y that will be k, or the slope, times that delta x that we picked. Okay, so then on Friday we built up what's called the point slope formula. We didn't call it that on Friday, but that's essentially what we did. So a function has a constant rate of change, and we know that constant rate of change is the same as the value of the slope, and it passes through the point AB. What's the definition of that line? And so the definition is basically saying what rule could we plug if we picked any x on the graph, say here, something a little bit less than -1, okay? But it can be any x. It could be here, it could be here, any x that we want. We pick any x, and we want to know what the corresponding output for y is. So we're saying, by creating a definition, we're saying, if I pick any x, what will the corresponding value of y be? What rule can I build with that input x that will crank out the corresponding value of y? So we start by looking at, starting at this point AB, we start by looking at, well, what change in x will we need to get from A to this roaming value of x? Okay, well, that will be delta x. And it's going to be final value minus initial. So in this case, that will be a negative delta x in the way I've drawn it, because delta x starts here and actually is represented by moving left. So whenever we calculate a delta, it's always going to be final minus initial. So final value of x minus the initial. So that's our delta x. And we said if it's constant rate of change, then changes in y are always a constant multiple of their corresponding change in x. And what is that constant multiple? Well, we saw that that's just the slope. So the corresponding change in y will be m times x minus a. So this, the change in y is that right there, will be m times the corresponding change in x, or m delta x is delta y. That was one of our big implications of changes being proportional. So finally, if we want this value of y, we start with the initial value of y, b. So the new y, there's the idea. The new y equals the old y plus the change in y. Okay, so I'll actually write the change in y first. The change in y we just calculated was this constant rate times our change in x. So this is the change in y. M x minus a change in y, plus what the old y was. The old y, the starting y, was b. And that gives us the new y. Okay, so this will generate, so given a point, AB, so that's a known point. These would actually be values. Okay, and you would know, somehow you would know the rate of change of the function. Then this can change. You can put in any x value we want, and by evaluating this expression, it'll give us the corresponding y value. Okay, I'm going to take this off. So here's kind of a summary. So when x equals a and y equals b, here's our definition. So to get to any point x, we're going to go through a delta x of x minus a. The corresponding delta y would be our constant multiple times delta x. Changes in y are constant times changes in x. We see that over and over again. And then we're going to start with the initial value of y and add the change to get our final value of y. So does it go through a, b? If we plug in a in for x, this is 0, and y equals b. So check. Function has slope m. Check. Okay, and just remember that that m, that's a value loaded with meaning, right? Loaded with meaning, that is our constant rate of change. Okay, so we want to do a piecewise linear function. What that means is we're going to actually be working with two functions, taking a piece of each and gluing them together. So synthesizing two linear functions together to create a new function that has a part of one linear function and a part of another. So we want a function that has a rate of change of 2. So we'll start with this here. We'll use our previous slide of the definition. As a rate of change of 2 passes to the point -1, 1. So let's just start out and write what that would be. So we know that y equals m, rate of change 2, times x minus initial value of x, which would be -1, plus initial value of y. And we worked that out in the last slide. Okay, so what we can do with that is we can make that into actually a function. And since that's going to be the first piece, we'll call it f1, the function f1. And this is comfortable because we talked about the idea that this definition requires that we choose a value of x, and the expression will crank out the corresponding y. So that fits the idea of a function perfectly, so we can just change y to be the output of our function. So the output of function 1 is the y value on this line. Okay, and so then abruptly at x equals 1, so this is the interval 1, 5, so this is x equals 1 and this is y equals 5. No, sorry, x equals 5. This is not an ordered pair, so I even got confused. Okay, this is an interval from 1 to 5. So 1 is our breakpoint. 1 is where this one ends. So again, this is the ending x value of the first one. Moving left to right on the graph, when we reach 1, this function will be done, and this function will begin at x equals 1. So we want to write this one as f2. This piece of our eventual function. So its rate of change is 5, x minus, starting x value is +1. Now the question here is, what y value are we starting at for f2 of x? Well, if we want to join these two pieces together, then the starting y value of f2 is going to be the ending y value of f1. At the change, at the breakpoint, we need the y value of this function. So how do we represent that? How do we represent the y value of this function at x equals 1? We can use our function notation to do that, and it will just be what we would get if we plugged 1 into this function. So it'd be f1 of 1. This way, if there's no guessing involved, this truly represents the y value of this first function at 1, and so now it becomes our starting y value for the second function. If I were to put 1 in for x, that would be 0, and our new function at x equals 1 would be the same y value as what it was at the end of that function. So we'll see a picture on the next slide that'll help. So here our function, two functions in pieces that we're going to piece them together to make one function. This piece will be for x from -2 to 1, and then this piece will be from 1 to 5. Okay? Let's see this visually and kind of summarize it. So here's this first line that we wrote, this is our F1 line. And we said that we want them to connect. So at x equals 1, so we can think of this as the y value here as what we would get if we plugged x into that first function rule, f1. But then we also want that to be f2 of 1, so that they match up and we have a continuous function, meaning that when we get to 1, whatever value we arrive at is the value we'll start at to continue on f2. So we built these in the last, we used point-slope formula twice, we built them in the last slide. Here was that first one that we built. It's exactly what we did. It represents this line here. And we say that here's the rule to get our y values for this line if we're between -2 and 1. If x is from -2 to 1. So that's our interval for f1. For f2, its interval is from 1 to 5. And just like we did, we got the rate of change, the new rate of change, it should be negative 0.5. And our starting value of y is the value of the function, or the y value at the finish value, the leftmost value, or breakpoint of the first function. So we use f1 of 1. Okay, we could put 1 in here and find what that value is. Let's go ahead and do it. So we could put 1 in, f1 of 1 equals 2 times 1 minus -1 plus 1, and that's 2 times 2 plus 1 is 5. So in this example, it'd be perfectly okay to put 5 there. It's just that we want to learn this technique because when we have complicated piecewise functions which don't have nice numbers, it's a lot more convenient just to always represent it this way, because we know exactly what that's telling us. It's telling us it's the value of the function, of the previous function, at the starting point of our new function. Okay, in this case at 1. So we want to learn to use that technique, although in this case that number is just simply 5, what we get when we plug 1 in there. Okay, and so here's how we put the two pieces together and represent it as one function. So now we've got one function. and we're just going to call that overall f of x. So f of x is made of our first piece, which is this one, from -2 to 1. And then once we get to 1, this piece takes over from 1 to 5. So does this function exist at, say, x equals -1/2? Well, -1/2 falls in this range. Since -1/2 falls between -2 and 1, to calculate the value f of -1/2, we're going to invoke this rule. Okay, what about at x equals 1? Okay, according to the way we set up the rule, when x equals 1, again, it falls here. Now, because of the way we set it up, it should give us the same value in both. But according to our definition, when x equals 1, again, we invoke this rule. What about x equals 3? X equals 3 falls in this range, so now we ignore this rule, and we follow this rule. We plug 3 into here, that the value f of 3 would be the output when 3 is plugged into that rule. So -1/2, I'm guessing it's 2. 2 times -1/2 minus -1 plus 1. This is 2 times, this would be 1 minus 1/2 would be 1/2 plus 1, so it is 2. So we got -1/2, 2. We know that when we plug 1 in we get 5, we already did that. If we plug 3 in, we're going to get 1/2 times, it should be -1/2. 3 minus 1 is 2, times 1/2 is 1, plus, we know that's 5, so I've lost track. 2 times 1/2 is 1, so it's going to be 5 minus 1. If we plug this in, we get 2 times -1/2 is -1 here, plus 5 will be -4. So at x equals 3, sorry, positive 4. So -1 plus 5 is positive 4, and that seems to be accurate right there. So that's our point 3, 4. And this is our point, -1/2, 2. So this is the idea of a piecewise function. We set the different intervals of the domain, and over this interval is where this rule applies. Over this interval is where this rule applies. So it still acts, in total, it acts as one function from -2 to 5, because any x value from -2 to 5 that we plug in here will crank out one particular output. It's just that it's going to use a different rule for different intervals of the domain. Okay, so that concludes what we got through in class on Monday, and your homework is to create one of these. I gave you the parameters in class, or on Blackboard. Let's see here. I gave you the setup to create one of these. So this practice, actually yours is going to be 3 pieces. You don't have to do any decimal approximations, and you don't have to compute any fractions. You want to use this type of setup using good function notation on our breakpoints. Okay, see you on Wednesday.